Hello everyone. Today we are starting on topics of electrical machine, and what we're going to do is we'll start with conducting material. So these are some materials that we have to understand electrical machine. So conducting materials, those are the material that have highest possible conductivity. They quickly flow electrons with them. They have least temperature coefficient of resistance. They have adequate mechanical strength. They have good rollability and drawability. Rollability means ability to make thin sheet out of it. Drawability means they draw them into thin wires. Next, resistance to corrosion, good weldability and solderability. Some examples are copper, aluminum, gold, silver. Next, most of the conducting material are copper, and the most electrical machine use copper in windings. Aluminum is cheaper and widely available, so the meaning is that we can use more aluminum in some works, such that the transmission line, cables and transformer tank we can use aluminum. Graphite is another material which is used as carbon brass, and this is not a metal, that is a carbon. Next type of material are magnetic material. So first is diamagnetic material. So they show a weak to no form of magnetism. They align opposite to applied electric field. That means when there is no electric field, H equal to 0, the dipoles are ideally placed. Okay, so they are in ideal mode. But when they are placed in a, say, they experience a magnetic field, dipoles will align opposite to them. Okay, so that means this is the direction of magnetic field, but dipoles are aligning in opposite direction. Next is paramagnetic material. So they show weak form of magnetism. So it is not that they will show no form of magnetism, they will show a some form of magnetism. So at H equal to 0, they're aligning in random direction, but upon placed in a magnetic field, they're aligning in same direction. Okay, so aligning in same direction means they're letting some amount of flux passing through them. Okay, so some examples of aluminum and air is a good example. Okay, so here air is a good example of paramagnetic material. So next, we are going to ferromagnetic material. So the ferromagnetic material, they show, say, the strong magnetic field. Okay, so ferromagnetic material means they are the strong magnetic field. So when no magnetic field is applied, the dipoles, they will combinedly align to a random direction. Upon application of magnetic field, they will align in the same direction of magnetic field. Then here you can see paramagnetic material, they are in random direction, and upon applying the magnetic field they will say align in same direction. Then diamagnetic, there is no say alignment, but when applied magnetic field they will show the opposite of it. So this ferromagnetic material, they are strong magnetic material. They have residual flux present. They have high corrosive force. They have exhibit pH curve. The type of material that are iron and nickel, they show, say, this ferromagnetic. They are ferromagnetic material. Okay, so they have classification as hard and soft magnetic material. And before that, we can go to another magnetic material, which is ferrimagnetic material. So it is slightly weaker than the ferromagnetic material, but the thing is that they are almost same. So here one thing is that uh, they can be used in high frequency transformer to reduce this hysteresis loss. Okay, so that thing we can continue. Okay, so continuing the discussion of transformer. So this is what a transformer, ideal transformer would look like. So there will be one primary winding, there will be one secondary winding. And from the primary winding, due to this winding, there will be some flux that will link through the transformer core, and this will call as magnetic flux phi, and it will link with the secondary winding of the transformer. So this is just the basic ideal transformer, but in depth of transformer, we'll have to say discuss about practical transformers. So the flux linkage will follow this some law. So one is Ampere circuital law. So what it will define? It will define that if the magnetic flux is in rotational direction, then the curl of our finger, if you are curling our hand, the thumb will give us the direction of electric current. Okay, so I think you already know, and we are just trying to sum it up. And this is also this is the representation of Ampere circuital law, and this is what solenoid looks like. If a current is flowing in circular direction like a solenoid, then here also you can put the direction of thumb. If you're curling our hand, and direction of thumb will give the direction of magnetic field. Okay, so now if we can see this, say, ideal transformer diagram. So here we can see this windings are in the solenoidal form, and if the current is flowing in the direction of our palm, then the thumb gives the direction of magnetic field. So this is just trying to understand the basic Ampere circuital law. Then this magnetic circuit and electric circuit both are analogous, and what we can see here is that current is analogous to flux, and magnetomotive force is analogous to electromotive force, and the flux density is analogous to current density, and similarly reluctance is analogous to resistance. Okay, so we can continue with the other terms also, and this is just the rough diagram of transformer. So the transformer, there are different type of transformer, but in general we can see this is the physical representation of a transformer. What it will have is that it will have the active part where the core and windings will be present. Then there will be these bushings, those are insulators, and the connections will be made through this, and this whole circuit will be submerged in coolant oil, and there will be a tank. So this is just one, say cross sectional area or cross sectional view of the transformer. Then there will be this conservator. There will be one relay called Buckles relay, and these are radiator just to release the heat from the oil. Then this is another good example of this transformer. So we are not going to go through this the physical representation of the transformer. Next, this core. So core is now made with laminated sheet. Okay. So as in the conducting material, or the say in the definition of metal, we can see some metals can be used to make a thin sheet out of it. So here this comes useful. So this one particular train will be insulated. That means both are not connected. Insulated through some insulating coatings, and here different type of say laminations can be used. So this E and I type of lamination, and this generally magnetic core is made of silicon steel, CRGO steel. Okay, CRGO steel has high saturation level, and silicon reduce hysteresis loss. So this is some say details about the materials, and there are some factors of net and gross say area that is important in electrical machine design, and the insulations are put between these two say every laminations. Okay, so these laminations are used to reduce eddy current. So that what is eddy current we'll learn in later say videos. So there can be many type of transformers. Generally, we can classify as single phase and three phase, and this is based on the windings. And another is from the structural type is core type and shell type. So shell type it will look like the core will cover the windings, and in core type the winding will cover the core. Okay. The significance are that core types is a series magnetic circuit, shell type is a parallel magnetic circuit. Okay, so here we can see this is a core type transformer, and generally in the ideal transformer we can show that there is one side there is primary winding and the other side there will be secondary winding. Just like this, consider this side is primary, this side is secondary. But in reality, the transformer windings are not say connected like that. So there will be low winding and high so low voltage and high voltage winding. So the low voltage winding will be connected near to core, and high voltage winding will be say connected further to the core. And suppose this side we have primary and secondary winding. So primary winding will be divided into two parts, secondary winding will be also divided into two parts. So that means this, suppose here low voltage winding is suppose primary, that means this primary winding is divided into two part, and secondary winding, suppose this say high voltage winding is secondary winding, so this high voltage winding is divided into two part and both will be the secondary winding. And there is different type of say winding type, sandwich winding. Here this is low voltage, low voltage, low voltage, and in between there is high voltage windings are sandwich. Okay, so this is important transformer insulation, and there is always a question about Buckles relay. So what is the use of Buckles relay is to say save the transformer from internal fault. Okay, so internal fault that can be happen due to breakdown of oil. That means if the oil get too much heated, that means the oil may lose the say cooling or insulating properties. So this is why this Buckles relay is used here. Okay. So we are not going too much about this. You can study about these points. Say they're like important from the construction part of it. Next, I have told you about transformer, ideal transformer. To understand a transformer, we have to start with the ideal one. So ideal transformer will have infinite permeability. Here iron loss is zero, resistance of the winding also zero, that means there is no loss. Whatever say power we are sending from this side, same amount of power will be received in the secondary side. Magnetizing curve is linear, that means this BH curve that we have already seen, here is this linear, and no magnetic leakage flux. Okay, so that means no loss, only direct power, same level of power will be transferred to the primary side to secondary side. Okay, so that is ideal transformer. Okay, so we already know that the transformer voltage and current can be like have a relation with the number of turns. Okay, we'll get that later also. And this is the relation of that the first what we consider is the flux is a sinusoidal flux. If you're providing a sinusoidal flux, then the EMF due to that sinusoidal flux will be n d phi by dt. That means we can put a minus sign, that is from the Faraday's law of electromagnetic induction. Then from that what we can consider is that this flux and this EMF are lagging. That means the flux will come first, then the EMF will comes later. Okay, and from this if we consider this 2 pi f uh, value, this 2 pi f, and we consider in RMS value, then what will get, the value will get that this formula or this constant value 4.44 will get from that particular expression only, 2 pi f by root 2, that is 4.44. And from that what we can get is that E1 by E2 is equal to N1 by N2, or E1 by N1 equal to E2 by N2. Okay, so this is the one basic say EMF equation of the transformer. So as we have seen about ideal transformer, this will be practical transformer. So what will the practical transformer will have? It will have finite permeability, it will some current will be required to set up a working flux, and that current will be called as magnetizing current. And this current provided by primary winding and exists under a no load condition. Okay, so this is what about practical transformer, and very important, a very actually very, what you can say, the practical transformer relations are very important. Okay, so here what is happening is that we are providing some amount of current to set up the working flux. That means, say in the primary winding, we are putting some particular voltage, and that particular voltage is providing some particular current I naught. This current will be always a very small value, and this current will flow in the winding, and it will have two components. One is magnetizing and one other is core loss component. Okay, so we can say different, so in different books we can see different say notations, but one is called as magnetizing, another one is core loss. So magnetizing will be related with the reactance, and then core loss will be related with the resistance. Okay, so that will be happening at no load. Okay, so that means there is no load provided in the transformer, and at this condition the secondary side will say develop voltage, but there is no load connected. That means there will be no such current. So in that ideal case, there will be I1 will be 0, I2 will be 0, but here the I1 will have, the primary current will have a component which is called as no load current component, and it will say have one magnetizing and core loss component of current. So in phasor, what we can say, we can show this phasor like this. So there will be some angle between this voltage V1 and I naught current, and this I naught current will be composed of IW and I mu. Okay, so here another important factor about this magnetizing or say no load current component is that at this point this value of this no load power factor phi naught will be very small. Sorry, not very small, this value will be very high. Okay, this phi will be very high, about say 60 to 70 degree of this say value will be around 60 to 70 degree. Okay, now second condition is called semi-ideal phase. Now what is happening here, you can see this I naught current. Okay, the phi naught angle is very high, and there is this I naught current. Now what will happen, the transformer that we had, there is no load connected. Now we have connected a load, a particular value of load. This load will have a secondary value of current. Okay, and this secondary current will provide a say mirror or say reflected what we'll call say reflection in the primary side based on the number of turns. Okay, so we already know this formula, I1 by I2, I2 is equal to N1 by N2. So based on that, we'll have a secondary, due to this secondary current, we'll have a primary current. And what already we had this I naught current, that is say no load current. Okay, that is composed of magnetizing current and core loss component of current. And adding both this to current, what will have actually primary current. Okay, so that means suppose we have a 20 ampere current developed in the secondary. Because of that, there is a 10 ampere current in the primary, but there will be already 2 or 1 ampere current or 3 ampere of current that will be called as no load current component, and this will be say added factor say there will be vector addition of these two current, and we'll get the actual primary current. Okay, so there is another thing is called as dot convention. A dot means these 2 points are considered as same polarity. Okay, so one dot the current will enter and another dot the current will leave. Okay, so this dot convention is considered for transformer in this way. From one dot the current will enter, another dot the current will leave, and both the dot will be in the same polarity. So now in practical transformer, what we can see is that there will be loss in the winding, there will be loss in the core, there will be a need of magnetizing current to set up the working flux, and there will be some leakage flux. Uh, with all this flux and those losses component considered, so what we can say, draw a phasor diagram of a practical transformer like this. So there will be one R1 X1, that will be the component of resistance, of winding resistance. R0 X0 will be the component of core loss, and R2 X2 will be the component of secondary winding. Okay, in that way we can draw a phasor diagram of all this parameter. And now there will be one term that is exact and approximate, say, phasor diagram. So this will be considered as exact. That means the components are placed exactly as the path of the current. But if we follow this particular, say, phasor diagram, what will happen is that we'll get difficulty in, say, doing our numerical problems. So what we can do, we'll modify all this into, say referred to primary or referred to secondary kind of phasor diagrams. And what we'll do, we'll make some, say, approximate equivalent referred to primary or secondary diagrams. I think you people all know about this. Now what will happen is that this is referred to primary. That means the component of secondary are, say, transferred to primary side, and the secondary side left with nothing else. So here what we can see, we are seeing primary winding, the core loss component, and secondary winding. So this is referred to primary, and this is, we can call as exact equivalent circuit. And now we can see here, this particular circuit can be called as referred to primary approximate equivalent circuit. That means we are doing some approximation and we are keeping only this particular component, core loss component, and we have considered as R01 X01 is a combination of primary and secondary winding, resistance and reactance. Now based on this, we can draw this particular phasor diagram. Okay, so what will happen is that first there will be flux will come in this direction, then along the direction of flux there will be a magnetizing component of current, there will be a core loss component of current, and based on this what we can see, IA. So before we have considered I naught, this IA, both are same thing. These are say no load component of current. And what will happen is that there will be a secondary current I2 will be say flow when we connect load, and because of that I2 there will be a mirror reflection in primary, and this primary current and this I naught will have vector addition and we'll get I1. Sorry, this is I2 dash. Okay, and that finally this I1 is the current component of primary, and based on this current component there will be I1 R1 that will be in the direction of current, because this is resistance, so resistance drop will be in the direction of current, and reactance drop will be 90-degree opposite to this, and this will be V1 E1. That means V1 is the primary, say, voltage connected, E1 is the EMF, and here E2 is the EMF that will provided by the secondary winding, and V2 is the actual voltage that is received by the load. Okay, so based on that we can have this vector diagram. So in the later we can discuss about this particular vector diagram in detail, but here what I am trying to do is that I am trying to give you a brief, say, idea of this particular say machine. So we are trying to get a brief idea about the transformer.